So this recording will include two sections, both 2.1 and 2.2. It made more sense to put them together because the material covered in 2.2 is more of a conclusion to the ending of the problem that we will do in 2.1. So finally, we'll start doing a couple things this week. We will be looking at defining linear first order differential equations and identifying when we have a first order linear differential equations and when we do not. We will also learn a technique in how to solve these linear first order differential equations. And then 2.2 extends a bit farther. After we find the solution and we have solved the differential equation, we are then going to tack on an interval for existence, where that solution or solutions can exist. All right, let's dive in. So a first order differential equation is said to be linear if it can be written in the following form, where you have a derivative function in terms of y plus some function in terms of x times y is equal to some other function in terms of x, where g of x and h of x are functions of the independent variable, typically seen as x, but can be t or many other different forms. And this form is called standard form for a first order linear differential equation. So if we take a look at these 6 differential equations, let's take a moment to apply the definition and to explore whether these are first order linear or not. And in order to do that, we will also have to practice putting them in standard form if they are not already. So for this first one, let's identify the two functions g of x and h of x. So if you look, g of x comes before the y. This is already in standard form. So I'm ready to go to identify. So this 2 in front of the y is the g of x. Notice it doesn't necessarily have to have an x in order to be a function in terms of x. Constant functions are very common. And what is on the other side of the equal sign is our h of x. And this is good practice for us to identify the pieces, as we will need that identification skill in order to use the method I'm going to show you this week to solve these things. Our y is written to the first power, and therefore this is indeed linear. Linear and first order. First order meaning that the derivative is just the first derivative, is the highest derivative in the differential equation. If you have y double prime, y triple prime, and so on, which indicates a second derivative and a third derivative, that's when you get to second order and third order. So first order part means what derivative to the first derivative is the highest derivative in the whole equation, and the linear has to do with the y part. So this y variable, or this y function rather, being to the first power makes this linear. And if we take a look at the second example, we have our standard form. This is in standard form, but it is not linear. And it is not linear because the y variable is raised to the second power, which is what constitutes it as not a linear first order differential equation. For this third example, let's first write it in standard form. And the reason why I know it's not in standard form is because the y is on the other side of the equal sign from the derivative. And in standard form, they are on the same side. So if I subtract that over, I get y prime minus 2y is equal to 0. So now this is standard form. I can identify the negative 2 as my g of x function, the 0 as my h of x function, and I see that the y is to the first power, making it linear. And it is first order because there's only the first derivative involved. Moving on to the next example. So first, let's put this in standard form. Okay, so I can see that this is h of x. It is a term that just has the x variable. And this piece here is the term that has the y, so we need to move that to the other side. So we'll get y prime minus cosine of x, y is equal to 1 over x squared plus 1, where this cosine of x is our g of x function. And again, we can see that the y is raised to the first power, making this a linear first order differential equation. For this next one, the y prime is equal to x squared. Because y is being multiplied by y prime, that will create things that are not just y to the first power and therefore not linear. And in this last example, if I take a look, it's already in standard form. My independent variable this time is t, and my dependent variable is x. How did I know that? You take a look at the derivative function to determine what is your dependent variable. Okay, all of these other examples had y prime, which therefore made x independent, and plus typically when we have x and y in an equation, that is usually how they go. But here we have x as our dependent, as it is x prime. So that makes t our independent variable. And so this would be our g of t, and this would be my h of t. And I look for the x in this term, and I see that it's raised to the first power, making it a linear first order differential equation. So those are the things that you need to look for as you are first identifying if it's linear in first order before you move on to solving these differential equations. In the future, we will have many different types of differential equations that we are handling, and not all can be solved with the same methods. Some methods will be very specific to linear first order, and others will be more general and can be used in a wide variety of differential equations. It is typically easier to use the methods that are for specific versions of differential equations versus using a more generalized method that is probably going to be more tedious and possibly more confusing. So it is really important that we can identify what type of differential equation we are looking at in order to then have our options in front of us of how to move forward when asked to solve. Okay. Now, when we want to solve a linear first order differential equation, one of the methods, and the method that we're going to explore this week, would be using this integration factor. Okay, so this integrating factor is one way to go about it. It's not the only way. If you did cover some basic differential equations in Calc 2, then the method that was taught in Calc 2, and again, I say if you did because it depends on the instructor on how much was covered and what was covered, but separable equations was introduced in Calc 2. And that is when we could separate the x's and the y's on separate sides of the equal sign and integrate respectively. That is one of the easiest methods for solving a differential equation. Unfortunately, being a separable differential equation is not always, one, that obvious, or two, that frequent. That's a very specific type of differential equation. So this is another method, and this is not for if your differential equation can be separated by x's and y's, then separable differential equation method would definitely be our go-to. It would be the easiest. But when we're looking at a differential equation that we are identifying as a linear first order and not necessarily separable, we will follow this method. So the first step would be putting it in standard form, which we've already had a little bit of practice in doing so when it was not already in standard form. Obviously, we would want to identify whether it was linear before moving on, because if this y variable is not raised to the first power, then this method is not useful. Identifying g of x and h of x would be next. Once we identify g of x, which is the function being multiplied in front of the y, we will then come up with our integrating factor. Our integrating factor will be denoted by mu of x. Okay, so this is the Greek letter mu, If you've taken a statistics course, you should be very familiar with this Greek letter, as it is typically denoting the population mean. But for us, mu of x is going to represent a function for the integrating factor using the formula, the function e raised to the antiderivative of the g of x function. No constant is needed in the integration. So even though this is an indefinite integral, and typically with an indefinite integral, we are required, hold on one moment, we are required to do a plus c at the end of integration. This is stating that we do not need a plus c for this particular integrating factor. That is not necessary, so we will not put plus c's once we integrate. Multiplying both sides of the standard form equation by this integrating factor will result in the following. So we will have the left side being the derivative of y times the integrating factor, and the right side being the h of x function that already existed times mu of x, the integrating factor. And I'll show you how this comes about as we go through these next couple examples. After we get the equation to look as it is in step 3, then we will integrate both sides. The best part about the left side is when we integrate the derivative, we literally just get what's in the brackets, so we're left with y times the integrating factor. And the right side, we will have to use our manipulation skills in order to do so. Note that after we integrate the right side, that's where we will put the plus c, not the left side. It doesn't really matter in the grand scheme of things, but eventually you're going to have to solve for y, so it makes sense to have the constant already on the other side. And you don't need two constants in one equation, which is why we don't need a constant on the left and the right. Now, this part is a theorem from 2.2, which we're going to discuss before we start solving these examples, because again, this is just an extension of the conclusion. And this is the existence uniqueness for linear first order in initial value problems theorem. So if we consider an initial value problem of the form in standard form, given some initial value x naught, y naught, we assume that g of x and h of x are both continuous on some interval between some value a and b, and the initial value exists on that interval. Then there exists a unique solution, y of x, to the initial value problem that is defined on this interval a to b. So the existence uniqueness for general first order in initial value problems, so not necessarily linear, states the same thing. So essentially what we will be doing is once we find our solution, we will analyze the solution. We will take a look at the x variable or the independent variable in the solution and determine what interval that makes sense for those inputs. So essentially it's like a domain, but it's a domain of an interval of existence is what we're going to call it. So with no further ado, let's dive right into some examples and walk through those steps in solving. And then at the end, we'll talk about the interval of existence. So our first example for solving is the differential equation dy dx plus 2y equals 0. Let me get my pen ready. Here we go. So the first thing that I want to do is double check that it's in standard form and that it's linear. So it is in standard form and the y is raised to the first power, so it's in standard form and it's linear. So step 1, standard form, check. Is it first order? And linear? Check. Okay. Step 2 is to create the integrating factor. Which recall is mu of x is equal to e to the integral of g of x dx without a constant needing needed once you integrate. So we recognize our g of x function being 2. So to get our integrating factor, we have e to the integral of 2 dx. If we integrated 2 dx, the antiderivative of a constant 2 is 2x. So our mu of x is e to the 2x, and again, no constant needed, so there is no plus c in this integrating factor. So e to the 2x is what we will need when we go to step 3, which is to multiply this integrating factor on both sides of the equal sign. So on the left side of the equal sign, we will multiply e to the 2x times dy over dx plus 2y. And on the right side, we will do the same, which is trivial because we are multiplying by 0. Now, on the left side, we have to first use our algebra, or essentially use our critical thinking to get it in the form, as I listed in the previous slide, where you have dy dx times y times mu of x. And so you know where that comes from. So this is going to transform into dy dx times 2y. Actually, it's just going to be y, not 2y. It's not the g of x. It's y times mu of x. So y times e to the 2x. Now, how do we get that? How do you believe me that that is a true rewrite and that I didn't change anything or solve anything? Why are those equivalent? Why is this form on the left side equivalent to this form? And it's because we are undoing the product rule. Take a look at what we're looking at. If I distributed this out, I have a derivative times a function, and I have a derivative times a function. So 2e to the 2x. Okay, that is the derivative of the y function. And so we undo that, and that's where the 2 disappears, right? So we have e to the 2x. If we take the derivative out, okay, so let me move forward. Maybe that doesn't make much sense. So take a look at what I'm looking at here. This is a product. If we took the derivative of this product, we would have the first times the derivative of the second plus the second times the derivative of the first. That is the product rule. And that is exactly what we're looking at in this step. Here we have the derivative, and here we have the derivative. So when you factor out the derivative, what you're left with is the first and the second function, e to the 2x and y. So essentially, we just undid the product rule. We took the integral. Well, we really didn't take the integral. We just undid it. We rewrote it differently because the derivative's still here. So we didn't integrate yet, but we factored out the derivative and rewrote the product rule back to its original form. So hopefully, since I went forward and showed you the product rule and how we got into the previous step, that helps you understand why these are okay to rewrite. Now, it's easy to remember if you don't necessarily see it clearly on how to go backwards. It's okay because I'm telling you that the left side, as long as you follow the steps in order and you have identified its standard form in first order linear, the left side will always rewrite to the derivative on the outside and the product of the two functions on the inside, the y times the mu of x. So now we integrate both sides. So step 4 is to integrate. So by integrating both sides and writing dx here, dx. When we integrate the derivative, we are left with just y times e to the 2x. When we integrate 0, the derivative of what is 0? Well, the derivative of any constant is 0. So we're literally just have a constant on the right side. And then lastly, step 5 is to solve for y. And so when we do that, we get y is equal to c over e to the 2x, or you can write this as c e to the negative 2x. Either one will work. This is called a general solution. Okay, let me actually clear this out so I have more room. Again, you can pause and continue your notes. So what we have is we have our general solution, y is equal to c e to the negative 2x. Where did that negative come from? Remember, the e to the 2x was in the denominator, and using our laws of exponents from our algebra classes, in order to bring the function up to the numerator, you make the exponent negative. So this is our general solution. Using the existence and uniqueness theorem, if we take a look at x and we consider, are there any restrictions on the input for x? And our answer would be no, there are no restrictions. And therefore, the interval of existence for these solutions is negative infinity to infinity. We'll use interval notation when denoting the interval of existence. Makes sense, interval, interval. And recall that you will always use curved brackets next to infinities, as infinity is not a specific number I can put my finger on. It is a concept of really small and really large numbers. Let's try another one. So for this example, we are going to solve the first order linear differential equation by following our steps. And step one is to put it in standard form. So I notice that it looks close to standard form, minus one part, which is the fact that this 3 in front doesn't belong there. So I need to divide all terms by 3. And then I get dy dx plus 4y is equal to 4/3. I am now in standard form. This has a derivative to it only includes the first derivative, so it's first order. And it is linear because the y is raised to the first power. So step one, complete. Step two, identify g of x and calculate the integrating factor. Okay, so we find that our integrating factor is e to the 4x. Again, no plus c is needed for the integrating factor. Then we multiply that on both sides. So we get e to the 4x times dy dx plus e to the 4x times 4y is equal to 4 times e to the 4x on the right side. Again, I can see that the derivative of the first and the second function is, this is the product rule. And I am just going to rewrite the product rule with, hey, if I take the derivative of the product of y and e to the 4x, I would get what the step was, the line above on the left side of the equal sign. And this is all equal to 4e to the 4x. Now that I have it in this form, I'm going to integrate both sides respectively. I need more room, so I am going to clear the screen and start at the top of the slide. So starting where we left off rather. So I'm taking the antiderivative of a derivative of a product, and I'm taking the antiderivative of the right side of the equal sign. So the left side, the derivative and the integral cancel, leaving us with y e to the 4x. Don't need to put the plus, we only need to put the plus c on one side of the equal sign. And since we're going to solve for y, it always makes sense to put it on the right side. And integrating 4e to the 4x is going to be a u substitution. Remember, any constants being multiplied by the functions can be taken out of the integral. So I am going to oh, wait, it's 4/3, right? Okay, I did mess that up. I was looking at the original equation, but this should be 4/3 because we had divided by that 3 a long time ago. So that 4/3 can be taken out of the integral. And then I'm looking at e to the 4x. I will let u be 4x. Some of you may be able to do this integration without actually writing out the u substitution at this point, since this is a very straightforward one. If not, a way to make sure we don't make those small mistakes is to write everything out. The derivative of u is 4 dx. So we make our u substitution. We have 4/3 times the integral of e to the u. And in order for me to accommodate 4 dx, I need to do some algebra manipulation here. I need to put in the 4. And remember, back when you learned this in Calc 2, that when you put in a constant into the integral, you are multiplying the whole thing by 4, which is illegal. You only can multiply by 1 because 1 doesn't change anything. So in order to balance this on the outside of the integral, I need to put a 1/4 because 1/4 times 4 is 1, and therefore I really just multiplied the right side of the equation by 1, and it doesn't change anything effectively. So I have 1/4 times 4/3 integral e to the u du now. And I then take the antiderivative of e to the u, which hopefully we all know is e to the u. So I get 4/12, which I will reduce, e to the u plus c, which reduces to 1/3 e to the 4x when I replace u with its original representation of 4x plus c is equal to this left side. We are ready to solve for y now. In order to solve for y, we will divide both sides by e to the 4x. Okay, I would like to give myself more room, but so you can see these are going to cancel. These are going to cancel, and your e to the 4x stays with the constant term, which results in the solution y equals 1/3 plus c e to the negative 4x, or c over e to the 4x. But again, I like to keep everything consistent in how you would like to write it, and I like writing it this way. When I am taking a look at that x input, again, there is no restriction, so my interval of existence will once again be negative infinity to infinity. Let's try another problem. Okay, let's try this example. So for this example, we have x squared times y prime plus xy is equal to 1. So step 1 is to put this in standard form. So the first thing that I'm going to want to do is divide by this x squared on all terms, as it does not belong there. And that gives me y prime plus x over x squared. It will cancel the x in the numerator and drop the exponent on the x to 1 in the denominator, giving us y over x is equal to 1 over x squared. Or, you know, I should probably write this differently because we have to identify g of x in the next step. So let me do 1 over x times y so that it's more clear what is g of x versus y. So now in my next step, I identify the g of x function as 1 over x. I then will create my integrating factor mu of x as e to the integral of 1 over x dx. The antiderivative of 1 over x is ln x, but remember from Calc 1, that there is a restriction on the inputs for ln functions. So when you take the antiderivative of 1 over x, you need to make sure to have absolute values in that natural log function. So we have e to the ln absolute value of x. Again, there is no plus c because we do not need a plus c for the integrating factor. Other thing to note is that e and ln cancel as they are inverses of each other, leaving us with just x and no more restriction of x because the absolute values were only necessary because we were inside of an ln function. The x now is fair game for any value. Now that we have our integrating factor as x, we multiply both sides of the equation by that integrating factor. So that gives us, let's see, we would have x times y prime plus 1 over xy, and we have 1 times x. Oh, excuse me, 1 over x squared times x. We know that the left side will reduce to y prime times the product of the integrating factor and y. And if we look at the right side, it simplifies to 1 over x. We are ready to take the antiderivative of both sides, or the integral. And the integral of y prime is left with the product xy. And again, the integral of 1 over x is ln of x in absolute values, and we add our constant in now. Last step is to solve for y, so I need to divide by x on all terms, giving me the solution y equals ln absolute value of x over x plus c over x. I only accept negative exponents in the e function because it's fairly common to have a negative exponent in the e function, but I do not accept negative exponents anywhere else. So it is not appropriate to write it as c times x to the negative 1. Keep that in mind. Now our interval of existence, one thing we know is that x cannot be 0 as it is in the denominator. We cannot divide by 0. And no, that does not change if we move the x to the negative 1. It still is the exact same concept, just rewritten. But it means the same thing. We also cannot include well, I guess we can include negatives because we have the absolute value inside of the ln function, but it is best to stay positive because of that ln function. And with those absolute values, we're not there as they were in some of the steps. Having all positive values of x would make sure that this was seamless and worked for all solutions. And therefore, the interval of existence will start at 0 and be any positive number. And it will not include 0, hence the curved brackets instead of square brackets, because 0 is not an appropriate value when x is in the denominator. Let's try one more example together. Our last example, y prime plus 2xy is equal to x cubed. It is in standard form, and it is linear as the y is to the first power. So then we identify g of x, and g of x here is 2x. We will use g of x to come up with our mu of x, our integrating factor. So mu of x is equal to e to the integral of 2x dx. The antiderivative, or the integral of 2x, is x squared. So we have e to the x squared as our integrating factor. Now, we will multiply both sides of the differential equation by our integrating factor. So we have e to the x squared times y prime plus 2xy is equal to x, I said x and I wrote e, x cubed e to the x squared. We know that the left side rewrites as y prime times the product of the integrating factor and y. And the right side stays as is. We are then ready to integrate both sides. The left side is straightforward. It is e to the x squared y. The right side is a product, which requires one of our rules that we learned in, or one of our techniques rather, that we learned in Calc 2. So for this one, I see that what is inside of the e function is not just plain x. On top of that, there is a product of functions. So this is going to be a combination of rules in order to solve. That combination will be a u substitution, or as I like to call it, a dub sub. I like to use a w when I know that the next step would be integration by parts, which the formula is written with u's and v's. Now, I'm going to give myself some more room before I start that part. So right now we are at the point where we have e to the x squared y is equal to the integration of x cubed e to the x squared dx, where I'm first going to do a w substitution for the inside function inside of e, where dw would be 2x dx. Now, where am I going to get that 2x from? Well, I cannot manipulate variables. I can only manipulate constants. So if I take a look at this x cubed, I hope we can all agree that this is equivalent to x times x squared. Laws of exponents, when you're multiplying the same bases, you add those exponents in order to get x cubed. So I can take one of these x's and put it where I need it for dw, and then I can input my 2 that I also need for dw by offsetting the outside of the integral with 1/2. So if I rewrite this, I now have e to the x squared y is equal to 1/2 integral of x squared e to the w. So let's not do the w substitution yet. 2x dx, where I will clarify that we have now formed dw for the substitution, and this x squared is w, and this x squared is also w. So remember, when you're doing a u substitution, in our case we're doing a w substitution, you cannot have the x's remaining. So this works out great because now our x squared is a perfect swap for our w. So now let's make the substitution, and I'm going to focus on the right side and stop writing the left side for now. So we have 1/2 integral w e to the w dw. Now that the function inside of the e function is a simple w and nothing else, we are ready for integration by parts. So we have w integral of w e to the w dw, and we need to assign u and dv for the integration by parts formula. So I'm going to let u be w because recall Lyot is the order in which you should assign things to the u part of integration by parts: logs, inverse trig, algebra, trig, exponential. Okay, that comes from Calc 2. So I know that my two options are algebraic, the w, or exponential, the e to the w. Well, since exponential is absolutely last and should be last to assign for u, and that's because the antiderivative of it is so easy, that's what makes my decision so easy to make w the u and e to the w dw the dv. Now we find du and we find v by doing the appropriate calculations. So the derivative of w is just dw, and the antiderivative of e to the w dw is e to the w. We then follow the formula for integration by parts. So we have u times v. So we have w e to the w. Oh, you know what? I'm missing a piece. I'm missing my 1/2 out front. I almost lost that from the last slide. So this is all multiplied by 1/2. So we have u times v minus the integral of v du is the formula. So minus the integral of v du. Awesome. Now in our integration, in our integral, we just have a single function that we can very easily take the antiderivative of. So we have 1/2 times w e to the w minus the antiderivative of e to the w is e to the w. And we will tack on our plus c now. Making some simplifications, or better yet, let's sub what we let w equal. And our w was originally, if we go back to the beginning of the problem, was x squared. So let's substitute that in. So we have 1/2 times x squared e to the x squared minus e to the x squared, all plus c. Notice I'm tacking the plus c onto the end because it's a constant that represents any constant. So manipulations of multiplying it by other constants like 1/2 is irrelevant. So altogether we have, you know what, new slide because I'm running out of room here. So putting it all together, we have the left side of the equal sign was e to the x squared y. And now the right side of the equal sign, if I distribute that 1/2, just so that I don't have any brackets, I have 1/2 x squared e to the x squared minus 1/2 e to the x squared plus c. Solve for y by dividing by e to the x squared on all terms. And we get the solution y equals 1/2 x squared minus 1/2 plus c e to the negative x squared. Again, the negative exponent for the exponential is perfectly fine. Now, when we take a look at the interval of existence, there is no restrictions on the x, so our interval of existence will be -infinity to infinity. Okay, and this concludes our lesson for identifying first order linear differential equations, solving it using an integrating factor, and identifying the interval of existence for all solutions.